Titrations are a very common lab technique, and I'm going to quickly go over some of the theory and do one practice problem for a strong acid, strong base titration. Now in grade 11 you would only really cover the strong titrations, and in grade 12 you would cover some weak acid, strong base, or weak base, strong acid titrations. So we're saying strong and weak, and that's based on the strength of the acid. Now remember, a strong acid dissociates completely and a strong base dissociates completely, meaning the acid will give its proton to the water molecule that it's dissolved in 100%. And because in a strong titration there's an equal strength between the acid and base, we can use the fact that we know the concentration is measured in moles per liter, which can then be rearranged for N equal to C times V. And we're going to define a new term here, equivalence point. This is the point in a titration when the molar value of the acid is equal to the molar value of the base. Knowing this, rearranging our concentration formulas for our acid and base, you know that at equivalence point the molar values are equal, and you can equate each side. This is very similar to the dilution formula, where you're just adding a new concentration or a new volume to change the concentration of something that you're diluting. Here, the volume of the acid and base will be independent, and the concentration factor will be key. So in a titration setup, you're going to have something that looks similar to this. A burette attached to a retort stand using a burette clamp. In the burette, you're going to put the solution that you know. So when doing this experiment with an acid and a base, you're going to know the concentration of one or the other of the species and use that number to find the concentration of your unknown. So this could be the acid or it could be the base in the burette, and then you have your unknown solution in an Erlenmeyer flask. Now, this knob here can be turned to very slowly add known concentration into your unknown solution. And the other thing that is a key component is in this solution there's going to be some sort of indicator. Now an indicator will change color at a certain pH range. For a strong acid, strong base titration, you're going to want to have an indicator that changes color as close to 7 as possible. As close to a pH of 7 as possible. So something like bromothymol blue that has an N point around 7 would be a great indicator for a strong acid, strong base titration. Often phenolphthalein is used when you're starting with an acidic solution and adding a base, but phenolphthalein's pH endpoint range is about 8 to 10, somewhere along there. So you've usually gone past the equivalence point in that titration for a strong acid, strong base. Now, this indicator choice will be very important, and you have to very slowly add your known solution, swirl the beaker around to get to that point, because it's going to go clear, and then you're going to get very close to the equivalence point where your molar values are equal, and maybe you see, so bromothymol turns blue, maybe you see blue start to form, and when you swirl it, it goes back to being clear. You're going to want to add that by increments, slowly getting smaller and smaller and smaller until you add a very small drop, could be half a milliliter, swirl the solution and it remains blue. Or if it's phenolphthalein, it remains a very faint pink and not a deep fuchsia color. So let's do an example problem. Here we're going to have a HCl plus NaOH. So these are our go-to acid and base, acids and bases that are strong. And we know that the concentration of the HCl is 0.15 molar, and we don't know the concentration of our NaOH. We're going to take 10 milliliters of NaOH and put it into our Erlenmeyer flask and slowly titrate the HCl that's in our burette into the NaOH solution. So the concentration of our acid is going to be 0.150 moles per liter, and that's going to be equal to the concentration of our base times the volume, 10.0 milliliters. I'm going to leave the unit in milliliters for now, and I'll explain why in a second. So in an example question, you were probably told it took a certain amount. So in this example, it said it took 15.4 milliliters to reach equivalence point. So here we're going to put in 15.4 milliliters for the volume of the acid. This would be experimentally determined or given to you in a quantitative practice problem. Rearrange this formula to isolate Cb, and you have 10.0 milliliters. Now, you could have written 0.01 liters, which would be more accurate because concentration is in moles per liter. However, I knew from reading the original question that both of these volume values would be in milliliters, and because you're solving for concentration in this rearranged formula, the milliliters will cancel out and you'll have your units remain moles per liter. Now, if that didn't make sense, just change your volume to liters. It's the easiest way to not make mistakes. 0.150 times 15.4 divided by 10 gives you the concentration of your base, which was 0.231 moles per liter. We had three significant figures for all of the things given in our problem, so that is our final answer. And the purpose of most titrations is to determine the concentration of an unknown acid or base. So in this example, we know that the concentration of NaOH was 0.231 moles per liter.